We have finished lesson 3 with the definition of a linear map, which is a function between vector spaces that has the property of being additive and homogeneous in the sense specified here. In this lesson, we're going to study this kind of maps in detail. Let's immediately see what happens when we apply a linear map to the null vector of a vector space. By definition, the null vector is the neutral vector with respect to the sum. That is, we can write every vector v as v plus the null vector. So, if we apply f to v, is like applying f to v plus the null vector. Using the property of additivity, we can write this as f of v plus f of the null vector. But as you can see, here we have the equality, if and only if this element here is the null vector of W. So to conclude, we have this, and then we can say that a linear map transforms the null vector of its domain into the null vector of its codomain. The next concept that we introduce is that of isomorphism. For this, I need to recall a couple of concepts related to functions that I think you already know. Given a function f from v to w, we say that f is one-to-one if, for every couple of different vectors, the images of f are also different. Instead, f is said to be onto if, for every vector of w, it exists at least a vector of v, such that the vector of w can be written as the image of the vector v through f. If we don't consider a generic function between vector spaces, but a linear map, which is asking more between these two vector spaces, which is one-to-one and onto, then this linear map is said to be an isomorphism between the vector spaces, and these vector spaces are said to be isomorphic via f. Let's immediately see with this theorem a very important example of identification between two vector spaces. If we consider again the map that we have discussed at the end of chapter 1, that is FB, where B is a basis of a vector space V of dimension n over the field F, then this map was defined as the transformation that sends any vector V into its set of components with respect to the basis B. Well, the theorem says that this map is an isomorphism. As a consequence, each time we fix a basis, a vector space with these characteristics is isomorphic to Fn, and we write this symbol here. What is fundamental is to underline that Fn is always the same vector space independently of V. For this reason, Fn is said to be the prototype of every vector space over the field F of dimension n. So, in particular, given a vector space of dimension n, if this vector space is real, then it is isomorphic to Rn. If it is complex, then it is isomorphic to Cn. It's important to underline that these two isomorphisms are created each time we fix a basis B of the vector space V. In fact, this is what allows us to construct the association between a vector and the components of this vector with respect to the basis B. If we don't have a fixed basis, we don't have fixed components, and so this association is not well defined. The great usefulness of this theorem is that V can be a very complicated vector space. However, when we fix a basis of V, then instead of working with the potentially complicated elements of this vector space, we can work with n-tuples of real numbers or n-tuples of complex numbers. The proof of the previous theorem is very easy. In fact, we have already proven that FB is linear. Now we have to prove that FB is one-to-one and onto. The fact that FB is one-to-one is an easy consequence of the fact that the elements of a basis are linearly independent vectors, and so every vector v is uniquely associated to its components with respect to the basis. Instead, the fact that fb is onto depends on the other property of the basis vector, that is, that they form a family of generators. So, as you see, the fact that the basis vectors form a linearly independent family of generators for the vector space V is absolutely fundamental to prove the isomorphism between V and its prototype Fn. We're now going to see an important consequence of this theorem, which unveils the fundamental role played by the dimension for finitely generated vector spaces. To discuss this consequence, we must recall the concepts of composition and inversion of functions. Let's start with composition by considering this diagram here. Imagine that you have three sets, x, y, and z, and imagine that you have two functions, f1 connecting x and y, and f2 connecting y and z. Then you can pass directly from x to z by operating the composition between f1 and f2. You build this composition by transforming x to the element y given by f1 of x, and then operating f2 on this element y. In one shot, as you can see here, you apply f2 to f1 of x. I reported here an example of composition, and I leave it to you to read it. Let me now pass to the concept of inversion. Let's consider a function f from x to y, which has the property of being both onto and one-to-one, as it is written here. If this is the case, then we can build the inverse of the function f, which is written with the symbol f minus 1, and f minus 1 reverses the order of the sets, and so it's defined over y, and it takes values in x. Its definition is the following. Every element y is mapped to x, where x is the only element that is transformed by f into y. Notice that x exists because f is supposed to be onto, plus x is unique because f is supposed to be one-to-one. So both properties must be satisfied at the same time in order to be able to define the inverse of a function. Here you can find an explicit example of inversion of a function. Notice that when a function is one-to-one and onto, we can ask ourselves what happens if we compose this function with the inverse. As you can see in this diagram here, first we have to transform x with f, obtaining y equals f of x. Then we have to apply f minus 1. And so we apply f minus 1 to y, but remember that f minus 1 applied to y gives back x. And so this function here is the function defined over x and which takes values in x that transforms x to x. So it doesn't do absolutely anything for all the elements of x. For this reason, it's called the identity function on x. The canonical symbol used to indicate it is id of x, and if you reverse the order, which means that you compose f minus 1 with f, you find the identity function over y. The concepts of composition, inversion, and identity will come back when we will deal with matrices. We can now use the concepts of composition and inversion of a function that we have just recalled in order to prove this result here. Consider two vector spaces V and W defined over the same field F, then they are isomorphic if and only if they have the same dimension. Suppose that the common dimension of V and W is n, fix a basis B1 of V and B2 of W. Then we can draw this diagram here. In fact, we can say that the vector space V and its prototype Fn are isomorphic through the function fb1 that we have defined in the previous theorem, and we can say the same thing for the vector space W, with the function fb2. Recall that fb1 and fb2 are one-to-one and onto, and so we can consider their inverses, this function here and this function here, respectively. Now, thanks to this diagram, we can show that V and W are isomorphic in two ways. For the first isomorphism, we have to follow the arrows that I'm underlining here in blue, this one here and this one here. The corresponding function is f of B1 composed with the inverse of f of B2. Instead, for the second isomorphism, we have to follow the arrows that I'm underlining now in red, this one here and this one here. And in this case, the corresponding function is f of B2 composed with the inverse of f of B1. Notice that in both cases we are building an isomorphism because we are composing isomorphisms. As you see, there is a key element for the proof of this theorem, and it's the presence of the prototype Fn for both V and W once we fix bases B1 and B2. In this section, we're going to see that linear maps allow us to build two noticeable vector subspaces. Precisely, given the linear map F between vector spaces V and W, we define the kernel of F, indicated with this symbol, the subset of V, given by all the vectors that are transformed to the null vector of W by F. Moreover, we define the image of F, indicated with this symbol, the subset of W, given by the vectors that can be written as images of vectors of V via F. Notice the difference. The kernel of F is a subset of V, and the image of F is a subset of W. Before showing that these two subsets are actually vector subspaces, it is better to say something regarding the kernel. Precisely, the kernel of a linear map is never empty. The reason is that, by definition of vector space, V contains the null vector, and since F is a linear map, it transforms the null vector of V into the null vector of W. Hence, by definition of vector space and linear map, we have that the kernel of F has at least the null vector of V inside. We can also consider the situation in which the kernel of F coincides with V. In this case, every vector of V is mapped to the null vector of W. That is, F is the null map. We can now pass to the proof of the fact that the kernel is a vector subspace of V and the image is a vector subspace of W. As we have already seen, in order to prove that a subset is a vector subspace, we have to prove the stability with respect to linear combinations. So, in the case of the kernel of F, we have to prove that if two vectors v1 and v2 belong to the kernel, then also the generic linear combination written here belongs to the kernel. The first thing that we have to remark is that if v1 and v2 belong to the kernel of F, then it means that F applied to v1 and v2 gives rise to the null vector of W by definition. So, if we apply F to this linear combination, by linearity, we find lambda 1 times F of V1 plus lambda 2 times F of V2. But F of V1 is the null vector of W, same for F of V2, and so we find a linear combination lambda 1 times the null vector of W plus lambda 2 times the null vector of W, which is, of course, the null vector of W. This means that when we apply F to the vector given by this linear combination, we obtain the null vector of W. That is, this linear combination belongs to the kernel of F, which is simply the stability of the kernel of F with respect to linear combinations. So, the kernel of F is a vector subspace. Let's now consider the image. If W1 and W2 belong to the image of F, This means that W1 is written as f applied to a certain V1 belonging to V, and W2 is f applied to another V2 belonging to V. Then, if we use the homogeneity and the additivity of the linear map F, we obtain the following. Lambda 1 times V1 plus lambda 2 times V2 is equal to lambda 1 times F of V1 plus lambda 2 times F of V2. However, by homogeneity, we can introduce lambda 1 and lambda 2 into these expressions, and then by additivity, we can sum these two expressions, obtaining this one here. So we have that this linear combination here is nothing but f applied to this linear combination of vectors belonging to V. This means that also this linear combination is the image by f of a vector of V. That is, this linear combination belongs to the image. We have proven that the image of f is stable with respect to linear combinations, and so it is a vector subspace. Having proven that the kernel and the image of a linear map are vector spaces themselves, it makes sense to talk about their dimensions. These dimensions have precise names written in this definition here. The dimension of the kernel of f is called nullity of f, and it is indicated like this. The dimension of the image of f is called the rank of f, and it is indicated like this. Let's immediately see why the kernel and the image of a linear map are useful. Let's start with the image. The linear map f from V to W is onto if and only if the image of f coincides with the vector space W. That is to say, the rank of f is maximal, that is, rank of f equals the dimension of W. For this reason, an onto linear map is also called a full rank map. The proof is immediate. In fact, as a nice and easy exercise, you can check that f is onto if and only if the image of f coincides precisely with the vector space W. If this is the case, then the dimensions of these two spaces agree, and so the rank of f is maximal. Let's now pass to the information provided by the kernel of f. The linear map f from V to W is one-to-one this time, if and only if the kernel of f is reduced to the only null vector of V. That is, if and only if the nullity of f is 0. To prove the theorem, we must prove both the direct and the inverse implication. Let's start with the direct one. Suppose that f is one-to-one, we have to prove that this implies that the kernel is reduced to the only null vector. We have already noticed that the null vector of V belongs to the kernel of f, which means that f applied to the null vector of V gives rise to the null vector of W. But since we are supposing that f is one-to-one, by definition, no other vector of V can be mapped in the null vector of W, otherwise f would not be one-to-one. This means that the only vector of V that is nullified by the action of f is the null vector of V. So the kernel of f is reduced to the null vector of V. To prove the inverse implication, we suppose that the kernel of f is reduced to the only null vector of V, then we must show that in this case f is one-to-one. Remember that f is one-to-one if it transforms different vectors in different images. So if we have two vectors such that their images are the same, in order to show that f is one-to-one, we must show that V1 and V2 coincide. Let's see how to do it. Notice that this equality implies that f of V1 minus f of V2 is equal to the null vector of W. However, thanks to the linearity of f, we can rewrite this as f applied to the difference between v1 and v2, obtaining the null vector of w, which means that this vector here belongs to the kernel of f. Notice that we have supposed that the kernel of f is reduced to the only null vector of v. Hence, v1 minus v2 is the null vector of v, but this is possible if and only if v1 coincides with v2. In conclusion, thanks to the previous argument, we have that under the hypothesis that the kernel of f is reduced to the only null vector of v, f is 1 to 1. Remember now that a linear map is an isomorphism if and only if it is 1 to 1 and onto simultaneously. Hence, the two previous theorems imply that f is an isomorphism if and only if it has a full rank and zero nullity. Let's now discuss a very important result on linear maps that is called the nullity plus rank theorem. The precise statement is the following. Given a linear map f from V to W, we have that the dimension of V is given by the sum of the dimension of the kernel of f and the dimension of its image. That is, the dimension of V is the nullity plus the rank of f. We are not going to discuss the proof of this theorem because it's quite technical. Instead, what we are going to do is to discuss the consequences of the previous theorem to a linear map for which the domain is equal to the codomain. Such a linear map is called an endomorphism. As a very nice and easy exercise, you can prove using the nullity plus rank theorem that if f is an endomorphism which is 1 to 1, then it is also onto, and vice versa. If this endomorphism is onto, then it is also 1 to 1. The very nice consequence is that if we have an endomorphism and we want to check if it is an isomorphism or not, we simply have to check if it is either 1 to 1 or onto. For an endomorphism, it is redundant to check both properties because one implies the other.
We have just seen that each time we have a linear map F between two vector spaces V and W, we can create two noticeable vector subspaces of V and W respectively. The first is the kernel of F, which is given by all the vectors of V, which are set to the null vector of W by the action of F. The second is the image of F, which is given by all the vectors of W for which it exists at least one vector of V that is transformed to W by the action of F. Using heavily the property of linearity of the map F, we have proven that F is 1 to 1 if and only if the kernel is reduced to the only null vector of V, and F is onto if and only if the image coincides with the vector space W. As an immediate consequence, F is an isomorphism if and only if both these properties are satisfied at the same time. Since the kernel and the image are vector spaces themselves, it is well defined to talk about their dimensions. The dimension of the kernel is called the nullity of F, and the dimension of the image is called the rank of F. These dimensions intervene in the very important nullity plus rank theorem, which states that the dimension of the vector space V is equal to the sum of the nullity and the rank of the linear map F. There is a category of linear maps for which the nullity plus rank theorem has very important consequences. These are the linear maps that are defined and take values in the same vector space V, and such a linear map is called an endomorphism. In the case of an endomorphism, the nullity plus rank theorem implies that this endomorphism is 1 to 1 if and only if it's onto, which is not the case for a general linear map.
In the following two examples, we apply what we have just learned by examining if an endomorphism of R2 is 1 to 1, onto, or an isomorphism. Let's start with the endomorphism F1, which applied on a generic vector of R2 written as x and y gives rise to x minus 1 and x plus 1. We have just seen that F1 is 1 to 1 if and only if its kernel is reduced to the only null vector, in this case of R2. In order to study the kernel of F1, we have to impose that F1 of x and y is equal to the null vector of R2, which has components 0, 0. By using the explicit expression of F1 of x and y, we can write this equation here as this one. This is a vector equation that can be rewritten as this system of linear equations here. Notice that the first equation implies that x is equal to y. If we introduce this information into the second equation, we obtain 2y equals 0, that is, y equals 0, and so thanks to the fact that x is equal to y, we have that also x is equal to 0. For this reason, we have that a vector of R2 written in the generic form x and y is nullified by F1 if and only if this vector is the null vector. For this reason, the kernel of F1 is reduced only to the null vector, and so F1 is 1 to 1. Since F1 is an endomorphism, it is redundant to study if F1 is onto, because we know that for an endomorphism, being 1 to 1 implies the fact of being onto. And so F1 is not only 1 to 1, but it is also onto, and so it is also an isomorphism of R2 with itself. Let's now consider the endomorphism F2. Notice that F2 and F1 are almost the same endomorphism, the only difference being that F1 had a plus sign here instead of the minus sign. In order to check if F2 is 1 to 1, we study the kernel of F2, and so we impose that F2 of x and y is equal to the null vector of R2. Using this expression, we find this vector equation, which is equivalent to this system of linear equations. However, notice that both equations that appear in this system are exactly the same, and in particular, they imply that F2 of x and y is nullified if and only if x is equal to y. As a consequence, we have that all the vectors that appear in the kernel of F2 have this expression here. Of course, we have the null vector, because the null vector has components 0, 0, they are the same, and so it belongs to the kernel of F2, as it should be, but there are an infinite amount of vectors that belong to the kernel of F2. All the vectors that lie on this diagonal belong to the kernel of F2 because they have the same x and y. Since the kernel of F2 is not reduced to the only null vector of R2, F2 is not 1 to 1, and so it cannot be an isomorphism. Let's check if at least F2 is onto. For that, we have to check that for every vector W written as AB in R2, there exists a vector V written as x and y belonging to R2, such that the equation AB equals F2 of x and y is satisfied. Using again the explicit expression of F2 of x and y, we can translate this equation into this vector equation here, which is of course equivalent to the system of linear equations. This system allows us to prove that F2 is not onto. In fact, as you can see on the right-hand side of these equations, we have two identical values, x minus y. Instead, on the left-hand side, we have a and b. Since a and b are free to vary in R, each one of them, we can choose a different than b, and in this case, we have one value different than the other, and it is impossible that two different values are equal to the same value represented by x minus y. This means that when we have a vector w written like this with a different than b, it is impossible to find a vector v written as x and y in R2 such that F2 applied to V gives rise to W, and so F2 is not an onto linear map. So the take-home message here is that even if two linear maps have very similar expressions, they can have a very different behavior. In this section, we study the surprisingly rich relations that we have between linear maps and bases of vector spaces. Let's start with this fundamental theorem. Consider a linear map F between the vector spaces V and W and a basis B for V given by the vectors V1, Vn. Then the theorem says that the images of the basis vectors via F, that is f of v1, f of vn, are a family of generators, in general non-free, for the vector subspace of W given by the image of F. The proof of the theorem is very easy. In fact, for every vector belonging to the image of F, there exists a vector belonging to V such that W can be written as the image of V by F. But since B is a basis, we have that the vector V can be written as a linear combination of the basis vectors, these ones here, through some coefficients lambda j written here. Hence, this equation here, using the linearity of the map F, can be rewritten in this way. That is, we can pass F through the linear combination in order to have this expression here. Now, since we have an equality, we can erase this element here, and we have W equals a linear combination of f of Vj. Since we took every possible vector belonging to the image of F, this means that every vector in the image of F can be written as a linear combination of the vectors f of v1, f of vn. So this family generates the image of F. We are now ready to state and prove the most important theorem of the section, this one here. Let's consider again a linear map F from V to W and a basis B given by vectors v1, vn for V. Then we have two statements. The first says that the map F is uniquely determined by the way it transforms the vectors of the basis B. That is, F is uniquely determined by the knowledge of the images of the basis vectors. This means that for a linear map, if we know how it acts on the basis vectors of a vector space, then we know how it acts on all the other vectors of the vector space. The second statement of the theorem says that once n vectors w1, wn are arbitrarily chosen in W, then there exists a unique linear map F from V to W such that Wj is equal to F of Vj. For both statements, notice that F is uniquely associated with the basis B that has been fixed. So, if we consider another basis, then also F changes. Let's prove the first statement. Consider any arbitrary vector of V, then we know that there exist unique scalars lambda j such that we can decompose V over the basis vectors Vj through this linear combination here. We also know that by linearity, the linear map F acts on V decomposed in this way as follows. That is, f passes through the linear combination and arrives here. Notice now that the scalars lambda j are uniquely determined by the choice of v and by the basis b that has been chosen, so the only action that is left to f is the way in which it transforms the basis vectors. Once we know how f transforms the basis vectors, then we know how f transforms any other vector v. Let's now prove the second statement, this one here. The proof is an immediate consequence of the statement that we have just proven. In fact, we have just seen that this expression defines in a unique way the linear map f, and so we just have to define f of vj to be equal to the vectors wj that we can randomly choose but fix, of course, in w in order to obtain a well-defined and unique linear map f. In the next page, I have highlighted two practical techniques that descend immediately from the last theorem. The first one is a practical method to extend a linear map from the knowledge of its action to the vectors of a basis to the whole domain vector space. The second is the practical method to build a linear map starting from the random choice of a suitable number of vectors belonging to the image vector space. Finally, if you think for a second, we have also acquired a very important information. That is to say, thanks to this expression and this expression, now we know that all linear maps are written as linear combinations of vectors belonging to their codomain. Of course, the best way to understand the theoretical results that we have just obtained is to use them in practice. For this reason, now we're going to discuss three examples. In the first example that we consider, we have an endomorphism of R3 represented by the linear map F that acts on the vectors of the canonical basis of R3 in this way. We want to find the general expression of the action of the linear map F on the generic vector v written as xyz of R3. Following the first practical method, the first thing to do is to decompose the vector v on the canonical basis in order to find its components. However, since we are dealing with the canonical basis, its components are simply x, y, and z. Then we must use this formula here in order to write f of x, y, and z as the sum of the components that we have just found times the images of the vectors of the canonical basis through f, as it is written here. If we replace these images with the data that we know, that is these vectors here, and then we perform all the computations that are written, we arrive to this vector here. This means that the extension of the endomorphism f previously defined only on the vectors of the canonical basis of R3 onto the whole R3 is this one here. As expected, when we use the canonical basis, the computations that we have to do are very easy. In this example, we're going to see what happens when we don't consider the canonical basis. Here we consider this basis B, which is the basis of R3 that we have examined in exercise 3 of chapter 1. So we already know that it is a basis of R3 and we don't have to check it. Then we consider the endomorphism given by the linear map G, and we impose that G transforms the basis vectors into the same vectors that we considered in the previous example. It's important to stress that thanks to the uniqueness property established in this theorem here, since G maps different vectors than the canonical ones into these vectors here, then G cannot be the same endomorphism as F. We are going to verify this in the next calculations. As before, in order to find out the generic expression of the endomorphism G, the first thing that we have to do is to decompose the generic vector of R3 with respect to this novel basis B. Since this basis is not the canonical one, we have to work a little bit more. In fact, we must write x, y, and z as the linear combination with coefficients a, b, and c of the basis vectors. By performing the computations, we arrive to this expression here, and by equating this vector here and this vector here, we find out this system of linear equations. As I wrote here, if we subtract the first and the third equation, we arrive to this equation here. Instead, you can see that we can rewrite the second equation like this, and if we introduce a written as y minus c in the third equation, we have this expression here. Then we isolate b by dividing both members of the equation by 4, and we introduce the expression that we find here in the third equation. By performing the easy algebraic computations that are written, we arrive to this expression here of the components of the generic vector v written as x, y, and z with respect to the basis B. As you see here, the expression of the components this time is much more complicated with respect to the components obtained by using the canonical basis. In any case, as you can see here, we can write the generic vector x, y, z over 3 as this linear combination here. These are the basis vectors that we have fixed by choosing the basis B, and these are the components of this vector here that will change as x, y, and z change. Now the last step consists in applying to both sides of the equation the function g. On the left-hand side we find exactly what we wanted, that is the expression of g over the generic element of R3. On the right-hand side we must apply by linearity g on the basis vectors, and the key to solve the exercise is to remember that we know the action of g on the basis vectors. In fact, the transformation of the basis vectors is given by this vector here, this one, and this one here. Now, in this expression here, we simply have a linear combination of these three vectors with the coefficients given by these expressions here in terms of x, y, and z. Notice that once we fix x, y, and z, these three expressions are simply real numbers. If you perform the computations that I have written here, you find out that the final expression of the action of G over the generic element of R3 is this one. Let us now pass to the third example, in which we show how to build a linear map by randomly choosing a suitable number of vectors of its codomain. Suppose that we want to build an endomorphism phi of R3. In this case, the codomain is R3, which has dimension 3, of course, and thus, if we want to build phi, we must fix 3 vectors of R3. I randomly chose these vectors here. From what we have learned before, we know that if we fix any basis of R3, we have that there is only one endomorphism phi that has these vectors here as images of the basis vectors. For simplicity, we first show how to build phi by fixing the canonical basis of R3. So our task now is to find the only endomorphism phi that transforms the canonical basis vectors into the vectors w1, w2, and w3. This job is of course simplified by the fact that the decomposition of the generic vector v written as xyz on the canonical basis is xyz. Hence, using the equation that is written in the second practical method to extend the definition of a linear map, we find that psi of xyz is simply written as x times this vector here, plus y times this vector here, plus z times this vector here. By performing the computations, we arrive to the generic expression of this endomorphism. Now recall that this construction is highly dependent on the choice of the basis. So, if we switch from the canonical basis to another basis, then the endomorphism that we construct is going to be different. We're going to do this with the basis B that we have considered in the second example. Luckily, we don't have to repeat the computations because in the second example we have seen that the components of the generic vector x, y, and z with respect to this new basis are exactly those which are written here. Hence, the expression of the novel endomorphism psi that we build using the strategy that we know is obtained by the linear combination of the vectors w1, w2, and w3 with coefficients given by the components that are written here. If you perform the easy algebraic computations that are written, you arrive to the final form of the endomorphism psi. By comparing the linear maps phi and psi, you can see that, as expected, they are different.
What we have just discussed underlines once more the importance of the concept of basis in linear algebra. In fact, we have just seen that in order to precisely know how a linear map is defined, we just need to know how this linear map acts on the basis vectors. Precisely, if we have a linear map f from v to w, and we fix a basis b given by vectors v1, vn, then we just need to know how f acts on v1, vn, and so the images f of v1, f of vn, in order to know how f acts on every other vector of v. For that, the first thing that we have to do is to take any vector v and decompose it on the basis vectors. We know that the coefficients lambda j that will appear in this decomposition are uniquely associated with the vector v. Then, in order to know how f acts on v, we just need to use those coefficients that we have previously determined, lambda j, and then multiply them by f applied over the basis vectors. We know that if we change vector v to another vector, then these components will change. However, the images of the basis vectors will remain exactly the same. So, once the images of the basis vectors via f are known, then f is uniquely determined. Vice versa, pick at random n vectors w1, wn belonging to w, then there exists a unique linear map f such that w1, wn are the images via f of the basis vectors v1, vn. This function is built with the same formula as before, however, we just need to replace f of vj with wj.